and welcome to another video. On the board are question 11A, 11B and C, 2010 S.S.C.E Section B, Part 2 Theory Exam question. Now the first question, which is 11A, is for us to distinguish between perfectly elastic collision and perfectly inelastic collision. Now, the first question we need to ask ourselves is, what is meant by perfectly elastic collision? And what is meant by perfectly inelastic collision? Then how can we distinguish between perfectly elastic collision and perfectly inelastic collision? Now, it is perfectly elastic collision when we have the collision in which kinetic energy and momentum are conserved. That is the case where we have the total momentum before impact, okay? That is, the total momentum, okay, before impact will be equals to the total momentum after what? After impact. Or the total kinetic energy before collision or before impact. That will be equals to, that is, kinetic energy before, okay, will be equals to the kinetic energy after. So this is in the case of perfectly elastic collision. Now, it is also perfectly elastic collision when we have what we call coefficient of restitution, because there's what we call to be equals to 1, because there's what we call Newton's law of collision of elastic bodies, where we have coefficient of restitution to be expressed as the ratio of the speed, okay, after impact to the what? To the speed before impact. Or we can say that coefficient of restitution can be measured as a ratio of velocity of separation to the velocity of approach, okay, between two colliding bodies. So when the value of coefficient of restitution is equals 1, then it means that the collision is what? Perfectly elastic. Okay, but when the value of E is equals to 0, then that means that the collision is perfectly inelastic. So that means the value of E lies between 0 and 1. That's it. All right. So what is now perfectly inelastic collision? Perfectly inelastic collision is a collision in which only momentum is conserved, but kinetic energy is not what? Conserved. That means energy is not conserved. That is because in the case of perfectly elastic collision, okay, the two colliding bodies will bounce off each other. Okay, while in the case of perfectly inelastic collision, okay, the two colliding bodies, okay, will stick together and move with a common velocity. That is, they will move with the same velocity after impact. So this is in the case of perfectly inelastic collision. Okay, and when we talk about coefficient of restitution in the case of perfectly inelastic collision, in this case, the value of E will be equals to 0, because coefficient of restitution is velocity of separation, okay, divided by velocity of approach. Okay, this is velocity of approach. Okay, why this is velocity of separation. So we have this to be velocity of separation. That's it. Okay, so to answer the question, okay, now 11A solution. 11A, 11A, there's our answer. So we have for perfectly elastic collision. Okay, perfectly elastic collision is a type of collision, okay, is a type of collision in which momentum, okay, and kinetic energy okay, are conserved, okay. Now let me put it this way: while perfectly inelastic collision is the collision in which momentum is conserved. Momentum is conserved. Okay, momentum is conserved, but kinetic energy is not conserved. That's Roman numeral 1. I'm going to treat this as Roman numeral 1. Now, Roman numeral 2. Perfectly elastic collision. Okay? Perfectly elastic collision. Now, let me put it this way. There is no energy loss. There is no energy loss. Energy loss during perfectly elastic collision. While in perfectly inelastic collision, okay, there is loss of energy. Okay, loss of energy in the form of heat, sound, and all of that. There is loss of energy. Okay, then we can also say that that is perfectly elastic collision. When it comes to perfectly elastic collision, let me have one more. Now, E is equals to 1 for perfectly perfectly elastic collision. Okay, elastic collision. Okay, however, E equals 0. Okay, for perfectly inelastic collision. Roman numeral 4. Okay, in perfectly elastic collision, let me put it this way. In perfectly elastic collision, the colliding object bounces off each other, whereas in perfectly inelastic collision, okay, the colliding objects, the colliding objects, the colliding objects, okay, the colliding objects stick together after collision. So that's it. So this is just to add to, the one I talked about. Okay, so perfectly elastic collision is a type of collision in which momentum and kinetic energy are conserved, while perfectly inelastic collision is the collision in which momentum is conserved but kinetic energy is not conserved. Okay, now there is no energy loss. So this just explains the first one here. Okay, there is no energy loss during perfectly elastic collision, while perfectly inelastic collision, there is loss of energy. So which means in the case of perfectly elastic collision, the total momentum before and after, that's before impact, will be equals to the total momentum after impact. Okay, so 11B, let's look at 11B. Sketch a distance time graph for a particle moving in a straight line with uniform velocity. Uniform velocity. Okay, in this case, just like when we say uniform velocity, the distance time graph of a body moving with a uniform velocity. Okay, we have distance versus time. Okay, so in this case, we know that the slope of the graph will be d over t. So this is the case of when a body is moving in a straight line with a uniform velocity, not with a uniform velocity. Okay, that means it's the body is accelerating from rest. That is when the body accelerates uniformly from rest. Okay, we know that the first velocity, which is the initial velocity, will be equals to zero. But in this case, we have a straight line passing through the origin. So remember, we are to use distance time graph, distance versus time. Then with variable velocity, that is the motion of a body moving under variable speed. Okay, in this case, we're going to have, it's going to be a parabola, something like this. It's going to be like a what? A curve. Okay, so the slope of the graph will be what? Will be what we call instantaneous velocity. Instantaneous velocity. It will be measured somewhere here. You know, when there's an abrupt change in distance with respect to time, then we have what we call instantaneous velocity. So the instantaneous speed in this case will be equals to small change in distance over time. Small change in distance over time. Okay, variable velocity. That's 11b. Okay, now we have 11c. For 11c, we are given that a body starts from rest and travels distances 120 meters, 300 meters, 180 meters in successive equal time intervals of 12 seconds. We are asked to determine each interval. The body is uniformly accelerated. Then calculate the velocity at the end of each interval and sketch a velocity time graph for the motion. Now, let's note this. Determine each interval. The body is uniformly accelerated. So now, during the first 12 interval, 12, during the first interval of 12 seconds, okay, the initial velocity will be what? Zero. Okay, so let's talk about the first interval. Okay, the first interval of time t equals to 12 seconds. So we have that the initial velocity will be what? Zero. So if the initial velocity is zero, so during the first interval, okay, we have d1 to be equals to 120 meters. d1 equals to 120 meters. So we know that t equals to 12 seconds. T equals to 12 seconds. So we need to find the acceleration and the velocity at the beginning of the second 12-second interval, because we have successive equal intervals of 12 seconds. So which means in this case, we're going to make use of the formula d equals to ut plus 1/2 of at squared. So during the first interval of 12 seconds, we have a1, okay, a substitute 1. So this will be, the first distance is 120. This will be 0 multiplied by 12 plus 1/2 of a multiplied by 12 squared. Okay, this will be 120. Okay, this will be 0 plus, this is 144. 144 divided by 2. 144 divided by 2, that will be 72. So this will be 72a. Okay, so that we can have 120 equals to 72a. Then the value of a will be 120 divided by 72. Okay, so let me divide this by 4. This is 30. Dividing this by 4, this should be, dividing this by 4, this should be 1 in 32, that's 8. Then divide this by 6, that will be 5. Then this is 3. So the acceleration is, during the first interval of 12 seconds, so the value of a is 5/3 meters per second. 5/3 meters per second squared. So now let's calculate velocity v1, which is velocity at the beginning, which will be the initial velocity, okay, of the second interval at the beginning of the next interval of 12 seconds. The next interval of 12 seconds. So that will be, we're going to have v1 equals to u plus at. Okay, so this will be v1 equals to u is 0. Then the acceleration is 5/3. Let's not forget at the time, okay, at equal time. So multiply by 12. So this will be 4 and that will be 20. So velocity, okay, the velocity at the end of the first interval, okay, at the end of the first interval, which is the velocity at the beginning of the next interval, is 20 meters per second. Okay, this is at the end of first interval, which is at the beginning of the what? The next interval. Okay, so that is for the first interval. Now, second interval of time t equals to 12 seconds. Okay, we have the distance to be 300 meters. So we have d2 to be equals to 300 meters. Okay, so t equals to 12 seconds. Okay, let's not forget that the velocity, which is the initial velocity, will now be 20. Okay, so we have that d2, so we're using d2 equals to v1 multiplied by t plus 1/2 of a2, because we need to calculate the acceleration, okay, in the next interval. So this will be t squared. So that this will be 300 equals to 20 times 12 plus 1/2 of a times 12 squared. This will be 300 equals to 240 plus 72a. So 300 minus 240 equals to 72a. So that a will be equals to 300 minus 240, that will be 60. 60 divided by 72. So the acceleration will be divided by 6. Okay, that will be 10 over 12 divided by 2. That will be 5 over 5 over, is it 12? 5 over, this is 60 divided by 70, 72. This is 10. This is 12. Okay, that will be 5 over 6. Acceleration will be 5 over 6 meters per second squared. That's the acceleration. Okay, the acceleration in the next interval. Okay, so I'm going to continue from here. So that's the, so now let's calculate the velocity. So we now have v2 to be equals to, v2 will be, so we calculated v1 here. So v1, we calculated v1 to be, so continuation. So we calculated v1. So this will be plus a2 times t. So this will be v2 equals to 20 plus 5 over 6, which is the acceleration, multiplied by 12. This is 2. So that v2, let me write it here, v2 will be equals to 20 plus 10. Okay, so that v2 will be equals to 30 meters per second. So this is the velocity, okay, velocity at the end of the second interval of 12 seconds, which is now the velocity at the beginning of the next interval. Let's put it that way, of 12 seconds. So that's 30 meters per second. Okay, so this is the second interval. So this one is for second interval because we are asked to determine the velocity at each interval. So this is the second answer, the second velocity. So now let's calculate V3. So to calculate V3, so let's know what is, okay, for V3, we need to first, so we have the distance of 180 meters, okay? So let's calculate V3. Okay, so we have D3. Okay, D3 to be 180 meters. T equals to 12 seconds. T equals to 12 seconds. Okay, so we are using 30 in this case. So we are going to use V3 to be equals to 30 meters per second. So that this will be 180 equals to 30 multiplied by 12. Okay, 30 multiplied by 12. Then one half of, so let's calculate the acceleration. One half of 12, this will be 360. So one half of the acceleration, okay, multiplied by 12 raised to the power of 2. So this will be 360. So I'm going to clean this part. So in this case, this will be 180 equals to 360 plus 72a. So that a will be equals to 180 minus 360. That will be 1 minus 180 divided by 72. So let's divide this. Dividing this by 6, this will be minus 30. Dividing this by 6, this will be minus 12. Okay, minus 12. Then divide again by 6. We're going to have a to be equals to minus 5 over 2 meters per second square. This is A3. That will be A3, the third interval. So now this acceleration, so let's calculate the velocity. Velocity will now be V2, okay, plus A3 multiplied by T. Multiplied by T. Let's not forget that T is equals to 12 seconds. So V3 will be equals to V2. We calculated V2 to be 30 meters per second. That's the second interval. So this will be 30 plus acceleration is minus 5 over 2 multiplied by 12. So that V3 will be equals to 30 minus, this is 6. 6 times minus 5. That will be minus 30. So first interval, okay, we have V1 to be equals to V1. We can use coordinates, but this is very important because the question will calculate the velocity at the end of each interval. So for first interval, we got that to be 20 meters per second. Okay, second interval, okay, we have V2. Second interval is 30 meters per second. Now, third interval, so we have V equals to 0. So that is, these are the answers for Roman numeral 1. Now, Roman numeral 2. Let me clean this part so that we don't. Roman numeral 2, that will be, for Roman numeral 2, sketch the velocity time graph for the motion. Okay, yes, the velocity time graph for the motion. So the first velocity is in velocity time graph. Velocity time graph. So we have the graph of velocity versus time. So we calculated the first speed to be, for the first interval, that's 20. So but the initial velocity is what? 0. So let's say this is 20. This is 20 meters per second. This is in meters per second. Okay, so this is 20. This is 20. Okay, then the second interval. Okay, let's say this is the second interval. This will be 30. Okay, then the third interval. So it decelerates to 0. So during the first interval, remember the time here is 12 seconds. Then the time here will be 12 plus 12, 24. 12 plus 24 plus 12. This will be 36 seconds. And with that, we've come to the end of this tutorial. The noblest pleasure is the joy of understanding. Bye-bye.